Now that we've defined inverse functions and found some ways of computing them, we're going to look more closely at determining when a function has an inverse, as well as how to find that inverse. So the first thing we're going to do is review the results of some problems from the previous in-class activities. So if you haven't done those yet, it might be a good idea to look at those so that the rest of this video makes a little more sense to you. We're then going to summarize what the results of those activities seem to say about inverse functions. And then we're going to use that to lead us to our main theorem, which we're going to state. We're not going to prove, at least not until the next video, but we are going to state our main theorem about inverse functions. All right, so in the in-class activities, we identified two issues that can keep a function f from a to b from having an inverse. So first of all, recall that if f inverse exists, our f inverse has domain B, which is the codomain of f, and the codomain is A, which is the domain of f. So the domain and codomain are switched for f inverse. So here was the first issue that appeared to be a problem for functions wanting to have an inverse. What if the function f is not injective? Now let's see what this, review what this means. A function not being injective means that we have two inputs, x1 and x2, whose outputs are the same. So f of x1 is equal to f of x2. So x1 and x2 are different, f of x1, f of x2 are the same. So let's review why this was an issue. And again, this was something that you explored in the in-class activities. So let's suppose that the y is the output for x1, so f of x1 is equal to y. And remember, since f of x2 is equal to f of x1, it is also equal to y. So y is equal to f of x1, y is equal to f of x2. Well, what does that say about our inverse function? Well, first of all, note that y is in B. So B is the codomain of f, so y is of course going to be in the codomain of f, but also B is the domain of f inverse, so if we wanted to, we could put y into f inverse. So the question is, what is f inverse of y? Well, remember, y is equal to f of x1. So f inverse of y is equal to f inverse of f of x1. But remember that f inverse and f cancel each other out, so that's going to be x1. And that seems all fine. It's like, right, wow, we figured out what f inverse of y is, but we could play the same game with f of x2. Y is equal to f of x2, so that means f inverse of y is the same as f inverse of f of x2. The f inverse and f still cancel each other out, and so we get x2. And so here's our issue. x1 is not x2, which is a contradiction. F inverse of y, because f inverse is a function, it can only have one output. And we just found that there were two. That means if f is not injective, which is what we were assuming, then f does not have an inverse. And if you want to take the logically equivalent contrapositive of that, if f has an inverse, then f is injective. All right, so here was issue 2. What if f is not surjective? Well, what does not surjective mean? That means there is a y, some element of the codomain, we'll call it y, that is not in the range of f. In other words, y is in the codomain, but it is not an output of f. All right, but if we're assuming that f inverse exists, what then would be f inverse of y? Remember, B is the domain of f inverse, which means that since y is in B, y is an input for f inverse. So what is f inverse of y? Well, let's see if we can figure that out. So we're going to let x be f inverse of y, and then we're going to find, then that means x is in A, since the codomain of f inverse is A, and so that means we could take f of x. Well, what's f of x? Well, we know x is f inverse of y, so f of x is f of f inverse of y. And the f and f inverse will cancel each other out, and that gives us y, which is an issue, right? We were assuming that we have that y is in the range of f, but we were assuming that y was not in the range of f because we were assuming that our function was not surjective. That's a contradiction. And so that means if f is not surjective, which is what we were assuming, then f does not have an inverse. And once again, if we take the contrapositive of that, if f has an inverse, then f is surjective. So if we want to summarize these two lines of thought, if f from A to B has an inverse, then f is both injective and surjective. Question, is the converse true? In other words, if f is injective and surjective, does f have an inverse? Well, that is something you're actually going to explore in the next activity, so I don't want to ruin the surprise. There's not going to be much of a surprise, but you're going to explore that in the next activities. One more observation about inverses, and in particular about how to compute them. So let's say we have f, the inputs are -3, -1, 1, 2, 3, and 5, and the codomain is 1, 3, 7, 8, 9, 10. And then we define f as a set of ordered pairs. Inputs are on the x coordinates, outputs are the y coordinates. So we worked with this particular function to find its inverse, and I was just asking you to find the inverse, and it turns out you were forced to conclude that the inverse was the following. And if you recognize the pattern between f and f inverse, all we did to get from f to f inverse was take the x and y coordinates and switch them. And again, you did a lot of analysis to figure out why we were forced to conclude that. That's not just something we did for fun and say that's the inverse. We used the definition, and we were forced to conclude that if 10 is your input for f inverse, then -3 was your output, for instance. And actually, let's see if we can recall how we did that, right? So if we want to find f inverse of 10, how do we do that? Well, we notice that from f of -3 is 10. So that means f of inverse of 10 is equal to f inverse of f of -3. The f inverse and f have to cancel each other out. That's just how inverses work, right? And so we get -3. So since f inverse of 10 is -3, we get the ordered pair 10, -3. And you can do that for the other ones as well. So all the analysis now that we've done leads us to two guesses about how to characterize inverse functions. First of all, since we're forced to, the inputs and outputs seem to be forced when we were looking at ordered pairs, it seems that you can't have a function with more than one inverse. Either a function doesn't have an inverse, or it does have an inverse and it has one. It has a unique inverse. And the other is that the inverse is obtained by reversing the x and y coordinates of the original function. Right? So right now, these are all conjecture, but we're going to go ahead and summarize that in, again, what is now mostly conjecture, but will eventually be a proof theorem. So let f from a to b be a function. Then, a couple things we're going to say. Well, maybe three things. F has an inverse if and only if f is injective and surjective. And we've actually proved half of that. We proved the if f has an inverse, then f is injective and surjective. The second is, if f has an inverse, the inverse of f is unique. In other words, the inputs and outputs are completely determined by f. You can't have any sort of choice of what your inverse is. And then, if f has an inverse, then f inverse is exactly what you get by reversing the x and y coordinates. In other words, f inverse, if we look at it as a set of ordered pairs, is a set of all b comma a in b cross a, such that f of a is equal to b. And just to understand, in case the last part of the conjecture is confusing to you, let me explain that a little further. So recall, if a, b is an f, then that means f of a is equal to b. So if f inverse reverses the x and y coordinates, in other words, it takes the x coordinates and makes it the y coordinates, makes the y coordinates, make those the x coordinates, then we have b, a, and f inverse where f of a is equal to b, right? F of a is still equal to b. All we did was take that same ordered pair a, b, where f of a was equal to b. We flipped the x and y coordinates, b, a, still true that f of a is equal to b. So you're gonna go ahead and finish proving. I said we. Really, it's you. You're gonna be proving the conjecture, the remaining parts in the class activities. And in case you want to know what those class activities are, it's called Finding Inverse Functions, and it's on the PDF file included with this video.